Great. Gee, not too many people coming to our session today. Oh well. Were you guys able to see the recorded Zoom session on La Lima? Megan, I can see you. Can you see did you see the video recording that was up on the La Lima site?
I actually didn't go check it out. I didn't feel that I needed to rewatch it.
Oh, okay. I bored you enough the first time?
No, I had the homework done, but it was good to like refresh it in my mind. Today I might play the recording though, because I'm a little confused.
Oh, okay.
Go write a sentence.
Daddy did not do this.
It's okay.
Okay, so I don't know if people are gonna come in later, but let's get started. So anyway, the first part of chapter 12 is kind of a review of what we did in chapter 3. You mix two things together. How do you know even something happened? Might be no reaction. So change in color, change in odor, you see some bubbles, you see a precipitate, change in temperatures. All those kind of things will tell us that a chemical reaction happened. And one concept that I'm trying to emphasize in a couple places here, some reactions are exothermic. That means that they give off heat. That means that the reactants have more potential energy than the products. Because of the conservation of energy, that energy will be given off. So if heat is given off, that tells you that a chemical reaction takes place, right? And then other reactions are endothermic.
Mag-aaral ka, right?
Pwede naman.
No, mag-aaral ka muna.
Hanggang 1:30 hanggang 3:30 to. Isa't kalahating oras to.
If I can mute that.
Kala ko online kayo. So paano ka makikinig dyan kung...
So I'm trying to, trying to find out where that sound was coming from. So some reactants, you mix them together, nothing happens until you increase the temperature. Because you have to supply kinetic energy to get those reactants up to the amount of energy that's in the products. So that reaction won't happen spontaneously just by mixing things. You have to actually put heat into it to make it happen. And so here's some way to predict what the products will be. And so I don't want to spend a lot of time on this, but I think I did a pretty good job of explaining this. Most books, you don't get that. So the point I'm saying is that we know so much about what individual atoms want to do to be happy, what molecules like to do. We can actually figure out what the products will be. So there shouldn't be any surprises. So I'm kind of going to skip that right now, the numbers, but look at this right here. Let's just go through the problem. So say I'm going to mix calcium nitrate with sodium phosphate. Now, on this side over here, can I put calcium together with nitrate again? The answer is no, because that would be no change. That would be no chemical reaction. So can I put calcium with sodium? The answer is no, because they're both positively charged. They're going to repel each other. So the only possibility is to put calcium with phosphate. And that leaves sodium having to react with nitrate. So we really just predicted what the products will be. So what I would normally do is Chemistry 100 wouldn't have to be able to do that. Biochem, I would want them to do that, but then I made the homework different. So I'm only going to do that on the homework. Matter of fact, I don't really know what I did on the homework because of all this virus stuff and everything. So then balancing reactions. And so here's an unbalanced reaction. Wait, right here. Here's an unbalanced reaction right here. So hydrogen and oxygen get together and they form water. So right now I have 2 hydrogens and I have 2 oxygens. So somehow they're going to have to go together and form 1 water molecule. But if I do that, how it's in blue right there, I have an oxygen atom left over. Oxygen atoms don't exist by themselves. In other words, this reaction isn't going to happen. But if I balance the reaction, so I ended up putting a 2 in front of the hydrogen, so that gives me 4 hydrogens. A 2 in front of the water, that gives me 4 hydrogens over here and 2 oxygens. And here's the 2 oxygens on the other side. So when I do that, I got the 4 hydrogens. I got the 2 oxygens. Here's 1 water molecule. Here's the other water molecule. Works out perfect. So really, why do we balance chemical reactions? It's really because of the law of conservation of mass. So guidelines for balancing reactions. And I say guidelines because a lot of textbooks will just say that, well, it's just trial and error. But there are some things that will really help you. So do a polyatomic ion first, because that balances more than 1 element at the same time. Do hydrogen and oxygen last, because if you do the other elements first, chances are oxygen and hydrogen will already be balanced. And then do elements last, because no matter what number you put in front of an element, you're going to change only for that particular element. So up here, if I would have put a number in front of the oxygen, I would have changed only for the oxygen. When I put the 2 over here, not only did I change for the hydrogen, but I also changed for the oxygen. So that's kind of the ace in the hole there. Do this last, because no matter what you put there, you affect only 1 element. Then play off of the molecule you just worked on. I'll have to demonstrate that. If it's even on one side and odd on the other, go for the product. If you get stuck, just start over with a different ion or molecule. So I did put step by step how to balance these particular ones, but there are different ways. You can do things in different orders. So for example, say I'm going to balance this reaction right here. Say I start with the nitrate. So here I got 2 nitrates. Over here there's only 1. So I could remedy that by putting a 2 in front of the sodium nitrate. And now, you see where the cursor is? I'm going to play off of what I just worked on. I just did the nitrate, so now I'm going to do the sodium. So if I had the 2 over here, I'd have 2 sodiums. So I come over here and 3 sodiums. That's not going to work. So instead of trying to make it work, I'm just going to go and do a different polyatomic ion. So I'll start with the phosphate. So here I have 1 phosphate, here I have 2. So I put a 2 in front of here. Now I'm going to play off of the molecule I just worked on. I'm going to go for the sodium. So I have 6 sodiums over here. So I'm going to put a 6 in front of the sodium nitrate. Now I have 6 nitrates. So I have 2 nitrates on this side, so I have to put a 3 over here. And after all that, I go to the calcium. I see the calcium is already balanced. So hopefully that gets the idea across. And then we're going to go through a bunch of practice, which I'm not going to go through all of them. At the same time, I'm going to try to explain to you what are the 7 major types of chemical reactions. So a synthesis or combination reaction is really some elements combined into compounds. So here's some elements combined into a compound. And a decomposition reaction is simply the reverse. A compound breaks down or decomposes into its elements. Okay. And then we have double displacement or double replacement reactions, where you have compounds turning into other compounds. And so when it comes to double displacement reactions, oftentimes they will use the solubility rules. The solubility rules will help us figure out whether the reaction will actually happen or not. So here are the solubility rules. I don't want you to have to memorize them or anything. But it says most salts of lithium, sodium, potassium, and ammonium are soluble regardless of the counter ion. So that means that, say, sodium chloride should be soluble. Sodium phosphate should be soluble. Most nitrates, nitrites, cyanides, and acetates are soluble regardless of the counter ion. Most chlorides, bromides, and iodides are soluble, but here are some exceptions. So, silver chloride is an exception. It's not going to be soluble in water. What about lead chloride? What about mercury chloride? That explains a couple of things. You could go out snorkeling and find a fishing weight that's made out of lead, and that lead could have been there for 50 years, and it's still in its native, stable, solid form. The reason is because this chloride in the ocean turns it into lead 2 chloride, which is not soluble in the ocean. So same thing with mercury, same thing with silver. They're not going to dissolve in the ocean because of the chloride. Well, sulfates are soluble. Some exceptions are with these ions over here. Maybe you know that barium sulfate is something that's used as a contrast element, taking x-rays of people's intestines. It won't dissolve in water, so it stays as a solution, and x-rays will be stopped by it. So most hydroxide and oxides are insoluble. And here's some other ones that are also insoluble. So really the way you should look at this is most things are insoluble unless the solubility rules tell you that it's going to be soluble. So here's an example of a double displacement reaction. I can tell that because there's a compound and a compound, and it turns into a compound and a compound. So the sodium is displacing the calcium, but the calcium is also displacing sodium. So they're just changing partners, essentially. So how would you balance this? Well, I'd go with the polyatomic ion. So I got 2 phosphates here, only 1 here, so I'll put a 2 in front of this. Now I'm going to play off of the molecule I just worked on, doing the phosphate, so I'll do the sodium. So now I have 6 sodiums on this side. I want 6 sodiums on this side, so I put a 6 here. Then I'm going to play off of the molecule I just worked on again. It's the bromine. So here I have 6 bromides over here. I have only 2 over here, so I have to put a 3 in front of this. So now the bromides are, how do you say, equal on both sides. So then I look at calcium. I got 3 calciums. Come over here, 3 calciums. Okay, we're done. So I look at the solubility rules. I see that sodium phosphate should be soluble because of rule number 1, that's sodium salts are going to be soluble. This should be soluble because of the rule about bromides. That should be soluble because of both of those rules. This one right here, phosphates. What did we say about phosphates? They're mostly insoluble unless the counter ion is from rule number 1. So there's no indication that this is going to be soluble. So I put the letter S there to indicate that it's a solid. So now, what happens? Sodium phosphate is soluble in water. Calcium bromide is soluble in water. I mix them together. A chemical reaction happens, and I precipitate calcium phosphate out of the solution. It becomes a solid. This is one of the indicators that a chemical reaction happened. So when you diagram a reaction, which is not normally done in chemistry courses, it really explains a lot. So when calcium phosphate precipitates out of the solution, the likelihood of it going backwards and dissolving again is nil. So you make the reaction happen up here, it leaves where the reaction is taking place. It doesn't matter how much you have here, whether it's a speck, whether it's a ton, whether you haul it away, or it doesn't matter. The reaction takes place here, and you've removed the product from where it's taking place. So that tells me that this reaction will happen.
And would any of that information help me in finding if the reaction will go from left to right?
Yep, if it goes from left to right, that means it goes to form product, right?
Mm-hmm.
So it will go from left to right because of the formation of that solid.
Right.
You can't go this way because that's not going to dissolve again.
Mm-hmm.
So another common practice is we write double and single replacement reactions in 3 different ways. The way we just did it is called the molecular equation. We wrote everything as a molecule. But another way to write it is called the total ionic equation. You write these things the way they would actually appear in solution. So sodium phosphate, we said, was soluble, so it's going to look like this. Calcium bromide is soluble, so it's going to look like this. Same with sodium bromide. But calcium phosphate is going to be a solid. So then the next step, or another way to write the reaction, is called the net ionic equation. What you do is you leave out all the spectator ions. So a spectator ion is something that's not involved in the chemical reaction. It's just watching. So for example, sodium. Here it's sodium ion. Reaction happens, it's still sodium ion. It didn't do anything. It's a spectator ion. Phosphate, on the other hand, is not phosphate on the other side. It's actually part of another molecule, part of their chemical reaction. And so really, sodium and bromide are the 2 spectator ions. If I leave them out, I can see what actually happens. So why does this reaction happen? Well, it's because calcium and phosphate go together to form a solid. So here's another one. Notice that here I have hydrocyanic acid, which is a gas. So I'm not going to bother balancing the reaction. I showed you how to do that here, but when you diagram it, this is what happens. You put all these things together, chemical reaction happens, you form hydrocyanic acid, which is a gas. The gas bubbles out of the solution. That's an indicator that a chemical reaction happens, right? Bubbles. So where does this gas go? Well, it leaves the container, fills up the room, goes out the door, goes out the window. Is it ever going to come back and go in here and reverse the reaction? The answer is no. So I see this happen. That tells me this reaction is going to happen. The reverse is not going to happen. Okay, so here's another one over here. And then single displacement reactions are a combination of an element and a compound, and it gives you a different element in a different compound. So here's a double displacement reaction, and here's a single displacement reaction. So if you look at the double displacement, calcium is kicking out sodium, but sodium is kicking out calcium. In a single displacement, sodium is kicking out lead, but lead's got nowhere else to go. It's just basically out by itself. Okay. So let me ask you a question here. What if I told you that sodium was a very reactive metal and that lead was much less reactive? Would that mean something? Don't all chemical reactions happen because there's something unstable? The reaction happens and now they become more stable. Right?
Right.
So an explosive material will blow up into more stable components, but those stable components don't automatically reassemble and go back into become an explosive.
Mm-hmm.
So if sodium is reactive compared to lead, when this reaction goes in that direction, the whole system becomes more stable. Okay. So now how would you know that, what's that doing? How would you know that sodium is more reactive than lead? Well, from your own experiences, do you ever find sodium metal anywhere? The answer is no. The only time you find sodium is when it's already in the form of an ion, like in sodium chloride. But lead, you know you can go to the hardware store and buy things made out of lead. It's a solid, it stays there, and it lasts for a long time. So that means that this reaction should happen. So some of the things in your daily life you know about. So the jewelry metals, for example, gold, iridium, platinum, silver, the jewelry metals are going to be stable, aren't they?
Right.
Hopefully no one will ever try to buy you some jewelry made out of sodium. It'd actually be quite dangerous. Or lead for that matter. So here's the activity series. Now you don't need to memorize this. I just want you to realize that you already know a lot of stuff. You know what metals are reactive and know what metals are not reactive. So up here is gold. And the way it's usually done is by looking at what does the ion do. So the standard reduction potential is in volts, which is given right here. And when it's a positive value, that really means that this is stable. When it's a negative value, it means that this is reactive. Okay. So gold is stable. All these ones over here are super reactive. So look at the ones that are stable. Gold, iridium, platinum, mercury, silver, copper, nickel, iron, lead, nickel again, cobalt, iron. You have an experience with iron. You also have experience with chromium and zinc. Chrome-plated things. Zinc is galvanizing. Okay? So say a galvanized boat trailer or something. It's steel, which is mostly iron, but it's coated with zinc. Okay, zinc becomes a sacrificial metal. zinc will get corroded before the iron gets corroded. So therefore your trailer is going to last a lot longer. So now in that previous example, we were comparing lead with sodium. Do you understand why that reaction happened now? So if lead is up here, basically I can make that reaction happen by putting anything in there that's more reactive than lead. So for example, any of these things over here. And why is it that zinc will protect iron? Well, here's zinc right here, and iron is over here. So if you have a boat trailer with both iron and zinc on it, which of those two is going to get reacted with by oxygen first? It's going to be the zinc. So therefore the zinc is a sacrificial metal. It will sacrifice itself to protect the iron. I can protect the iron with anything that's more reactive than iron itself. Anyway, so why will this reaction happen? I'm comparing copper with silver. Which one is more stable?
Silver.
Silver. So yes, this reaction will happen because I'm making a metal that's more stable. Here I diagram this reaction over here, copper and silver nitrate to give you elemental silver. So silver nitrate solutions were used a lot in the old-fashioned black and white photography. That was before they had cameras on cell phones, right? Yeah. So they had all these solutions of silver nitrate around, and somebody said, hey, if I could find a way to recover all that silver, I would be extremely wealthy. So, what's more reactive than silver? Here's silver right here. I could put anything that's more reactive than silver in there, and I can make silver precipitate. So copper is more reactive than silver. So when I put a copper plate in here, the copper loses its electrons and gives it to silver because silver element is more stable. Make sense?
Mm-hmm.
So some of these are closer. You would have a really hard time figuring out what's more stable, zinc or aluminum. Same thing here, except you know about iron, you don't know much about magnesium. What if I told you if I took magnesium metal and I put it in a flame, like in a candle, it would burn. But iron won't do that. So that means that magnesium is less stable, right? It's more reactive. So is this reaction going to happen? You're going from stable to reactive? No, that reaction is not going to happen. The reverse of that reaction would happen, though.
So on the homework, we would say that it doesn't go from left to right.
Exactly, right. Okay. So anyway, I gave some other examples over here. And here's a $1 billion ship that was produced by United States Navy and all these engineers and everything, and they still had some corrosion problems. So here's another type of activity series used by people like these. So you can see that magnesium is extremely reactive. you have steel over here, copper over here, stainless steel over here. You know stainless steel is more stable than regular steel. What they really do is they replace a lot of the iron atoms with nickel. Nickel is more stable. So here's nickel up here. Here's silver, here's gold and platinum, and then finally graphite. So now the concept is go replace this corrosion problem with graphite, which I don't know why they didn't do that to begin with. But they all make a lot of money off of the government. And so I thought I would put a concept of batteries in this chapter. So here's a battery. Here's a picture of the battery. And here's the overall reaction. Here's the net ionic reaction. And you can see that electrons are going from the zinc to the copper. Now, why would that happen? Because zinc is more reactive than copper. So over here, we have a high potential energy. Over here, there's a lower potential energy, which is what a battery does, right? It stores potential energy as a chemical reaction. So if we look at this battery, here we have zinc, and here we have copper. Now, anytime you take a wire or something like that and put it into a solution, that's now called an electrode. So we see that zinc is losing electrons to the copper. But here, the electrons are going through the conductive copper into the solution, where the copper ion right here is accepting those electrons and turning into copper the element. So this electrode right here is actually getting bigger. We go to this electrode over here. In order for the electrons to leave the zinc and go this way, the zinc has to turn into the zinc anion. So what's happening to this electrode over here is that it's decomposing, it's getting smaller, it's dissolving. So what's happening on this side over here is you're getting more and more zinc +2 ions. So over here would get more and more positively charged. Over here, positive charge is disappearing and you have negative charge coming in, so this is getting more negatively charged. But in fact, that cannot happen because every piece of matter has to be electrically neutral at all times. So notice that here you have electrons coming in over here as a regular current. And to prevent that from getting negatively charged, the sulfate ion has to travel through this thing called a salt bridge to get back to the other side, to keep both sides neutral. So this is called a salt bridge or a chemical bridge. So you have two types of current. One is a typical electrical current, and the other is a chemical current. Why does this battery give energy off? Because zinc is more reactive than copper. And as the electrons travel through this wire, I can make them travel through a motor, through a light bulb, whatever, and get energy out of it. Any questions so far? You know, Zoom is a very dangerous teaching tool. I can go over here and I can manage the participants. I could ask them questions, but I won't do that. Just do whatever you're comfortable with, okay? So anybody have any questions?
No.
So here is your car battery. No, I didn't mean I took it out of your car. This is a car battery. And it's a little bit more complicated because if you look at the overall reaction over here, you have lead on this side and lead on this side. If you look at the net ionic equation, you have lead, the element over here, and over here there's no lead element. This is lead plus 2. So here's lead plus 4, here's lead 0. Electrons are going from the lead to the lead plus 4 and turning into the lead plus 2. A little bit more complex. So if you look at your car battery, the lead oxide is what's on here. It's the lead electrode coated with lead oxide. And if you follow this, it does not interact directly, it doesn't come into direct contact with the other electrode. The other electrode is simply lead. So the electrons go from the lead to the lead 4 in terms of the lead 4 oxide. So it may seem complex, but the one thing we know about car batteries, you put them in your car, they last for years, they can be knocked around, they can be hot, they can do all kinds of stuff and still survive. You go back to something like this, that's not going to be a very good car battery. Here's an alkaline cell. Here's the chemical reaction for the alkaline cell. So electrons from elemental zinc goes to the manganese 4. So electrons go from here to here. And so here's the zinc, here's the manganese, right? And so how they get there, it has to travel through a wire going this way, and then you put some machinery in there. It could be a battery, it could be, I mean, not a battery, it could be a motor, it could be a light bulb, whatever, and it turns it on because of the flow of electrons. So can you determine reactivity from the periodic table? Yes, you can, but it's not a simple thing, which is why they made the activity series. Yeah, I'm trying to keep my eye on the chat as well. Okay, questions before we go into the next type of reaction?
Nope.
Okay, so acid-base reactions are neutralization. What really drives them is acids produce H+, bases produce OH-, and those two are going to like each other. They're going to fall in love, and when they do, they make water. So, what is an acid? In an acid, we'll always have at least one hydrogen in front of the formula, and they always produce H+ in water. And bases will have a hydroxide in the formula. So neutralization, you're trying to produce water. So here's an acid. Later on, we'll see it's called hydrochloric acid, and that H+ goes from the acid to the base. And what does it do? It makes water. So notice that I have 2 hydroxides in the magnesium hydroxide. I got 2 hydrogens all together over here, so I'm going to make 2 water molecules. When I do that, what's left over is the magnesium ion and the chloride ion. So it's going to make magnesium chloride. So you can balance these kind of reactions just like how we did before, but a different way of doing it, maybe a little bit more insightful, is to look at the hydrogens and to look at the hydroxides. So for example, before it's balanced, I see that I have 2 hydroxides here and 1 hydrogen over here. Is that going to be able to go and make 1 water molecule? The answer is no. For every hydroxide, I need 1 hydrogen. So I have to put a 2 in front of here so I can get my 2 hydrogens. Now I have 2 hydrogens and I have 2 hydroxides. That should be able to make 2 water molecules. So I put a 2 over here. So this is a different way of balancing. This only works for acid-base reactions. I think it's very effective. So if you look at the molecular equation versus the total ionic equation, honestly, you have to know a little bit more about acids. But acids ionize. You put them in water. So the HCl would turn into H plus and Cl minus. This is soluble because of its magnesium. Other hydroxides wouldn't be soluble. And then water is simply water. It is a molecule. And then this would be a soluble ionic compound, so you get magnesium and 2 chlorides. Then if you throw out all the spectator ions, which would be the chloride ion on both sides, the magnesium ions on both sides, then you get the net ionic equation, which shows you what really happens in a neutralization reaction. You're just forming water. Why does it happen? These are reactive, water is stable. So I did a couple more there. And then we get to combustion reactions, which is described as a combination with molecular oxygen. So you're doing this right now. Maybe you know that. So here is glucose. You ate glucose, you're breathing in oxygen, and what are you exhaling? CO2 and water. And you do this because it produces energy that you need to run your body. So I started off by showing you the burning of magnesium. And maybe you're thinking, what? A metal can burn? Yes, the metal can burn. If I take magnesium and simply put it into a flame, it's not going to happen right away, but eventually it's going to catch on fire. I take it out of the flame and the thing is burning by itself. Now, if I were to take iron and put it in the flame, I wouldn't really see anything happening. But what is rust? Rust is a combination of iron and oxygen. Rust is iron oxides. So that also is a combustion reaction. But oftentimes we talk about hydrocarbons. So for example, this right here is called methane. If you burn methane, you'll use up oxygen. And if you burn up all the way, you'll get carbon dioxide and water. If you don't have enough oxygen, you might get some carbon monoxide, right? Which we talk about as being a pollutant. So with these, the last thing you're going to do is put a number in front of the element. And we also said that you should do oxygen and hydrogen last anyway. So that means that the first thing you should do in a reaction like this is going to be the carbon. One carbon, one carbon. Okay. Then I'm going to do oxygen last, so I'll go to the hydrogen. 4 hydrogens, only 2 hydrogens. So I have to put a 2 there. Okay. So now I have 2 oxygens here, 2 oxygens here, so there's 4 on this side. I need 4 oxygens on this side, so I had to put a 2 there. So now it's balanced. Make sense?
Yep.
Then we'll go to one that's more difficult. So this right here is butane. So butane requires 13 oxygens, right? To burn, and I get nothing but CO2 and water. Let's go through the process. So I'm going to start with carbon. 4 carbons, only 1, so I got to put a 4. Then I have to go to the hydrogens. So I have 10 hydrogens over here. I would have only 2 over here. So I had to put a 5 in front of the water. So now I have my 10 hydrogens and my 10 hydrogens. Now what number do I put in front of the oxygen? I got 8 oxygens plus 5 more, so that's a total of 13 oxygens on this side. So I'm going to multiply by 13 halves, because 13 halves times 2 gives me 13. So this right here is balanced. But you may be uncomfortable with the idea of having 6.5 oxygen molecules. We know we can't have half of an oxygen molecule. So, because this is balanced already, like any kind of a mathematical equation, if I want to get rid of that 2, I can multiply both sides of that equation by 2. So the whole equation. So that's how I got the 2 over here, the 13 over here, the 8 over here, and the 10 over there. Now, isn't that happy?
Yes.
They're not necessarily happy. It's chemistry, okay?
Okay.
It's chemistry. Don't expect to become happy.
Or awake.
Yeah, or awake, yeah. So then our last type of chemical reactions are redox reactions, or oxidation and reduction. And so, how do you find out if a chemical reaction is a redox reaction? Well, like we did in chapter 9, we can assign oxidation numbers. So anytime you see a change in oxidation number, it's a redox reaction. That means that something gained or lost electrons. So one thing that really shows that clearly is if you see an element on one side, and then on the other side, it's an ion. Does that make sense? So if you see getting a more positive oxidation number, that means that it lost electrons, it got oxidized. If you get a more negative oxidation number, that means it got reduced, it gained more electrons, which are the negative charge. So oxidation is the loss of an electron, the loss of a hydrogen atom because the hydrogen atom contains an electron, a gain of an oxygen atom because oxygen is so electronegative, it will pull electron away from anything. And oxidation is you get a more positive oxidation state. And reduction is the exact opposite. So let's look at this reaction right here. So here's copper. Its oxidation number is 0 because it's an element. Here's silver. So silver is the +1 and nitrate is the -1. And here's copper. And because nitrate is a -1, right? Copper then has to be a +2. Here's silver, it's an element, so its oxidation number is 0. So now that we have those assignments, I see that copper goes from 0 to a +2. So what happened to copper? Got oxidized. So that means that this is a redox reaction. What happened to silver? It went from a +1 to a 0. That means it got reduced. So I can see the electrons going from the copper to the silver. And the reason why that would happen is because silver is more stable than copper. And what did the nitrate do? Not much. Spectator ion. Okay. So to find out if this is a redox reaction, all you have to do is see one oxidation number change. The easiest way to do that, if you see an element on one side and on the other side it's not an element anymore, it's a redox reaction. So what that means is that all synthesis, decomposition, single replacement, and combustion reactions are all redox reactions. So I showed you here how assigning oxidation numbers can help explain all the things that are going on. So here I did it in a chemical reaction form with just the molecular formulas. So the oxidation numbers have to add up to be 0 for methane, right? Because that's a neutral molecule. So if the most electronegative element between carbon and hydrogen is going to be carbon. So carbon gets the negative number and hydrogen gets the positive number. So the only positive possibility on the periodic table for hydrogen is going to be a +1. So that means that carbon has to be a -4. And oxygen is a 0 because it's an element. And for carbon dioxide, oxygen is much more electronegative than carbon. So oxygen has to be negative, carbon has to be positive. So if oxygen is a -2, carbon has to be a +4. So similar type of thing with water. So now I've assigned all the oxidation numbers, I can see what happens to every single atom. Carbon went from a -4 to a +4. So it got oxidized. What happened to the hydrogen? It went from +1 to a +1. Nothing happened to the hydrogen. What happened to the oxygen? It went from a 0 to a -2. So it got reduced. So say you're methane. Methane just got oxidized. What kind of a molecule, what kind of a substance oxidized it? Maybe an oxidizing agent. So as we know, oxygen is a very powerful oxidizing agent. Now your oxygen, you just got reduced. What kind of a molecule reduced you? Maybe a reducing agent. So in this reaction, methane is a reducing agent. And this is a redox reaction. Then I took that same thing and I put everything in terms of complete Lewis dot structures. So you can see that every single atom now has an assignment. You see that everything works out. So here's the rusting of iron. This is a combustion reaction. Can you see that?
Yes.
Reaction with molecular oxygen. So iron got oxidized and oxygen got reduced. So the electrons flowed from the iron to the oxygen when we formed iron 2 oxide or iron 3 oxide. So here's redox reaction, because I see that aluminum starts off as an element and it ends up as an ion. It ends up as the +3. That's enough to know that it's a redox reaction. Here's a double displacement. And double displacements are not redox reactions. So to prove that to you, I assigned all the oxidation numbers, and then we look and see if there's anything that changes. Calcium is a +2, +2. Chloride -1, -1. Sodium +1, +1. Carbonate, carbonate. Nothing changed. Not a redox reaction. So questions so far?
In the redox reaction, what if there's only a reduction? Then it's not a redox, right? Because there is no oxidation.
So that can't happen.
Mm-hmm.
Because of the law of conservation of mass, electron can't just disappear. So if something loses an electron, there has to be something there to gain the electron. Okay?
Got it.
Okay. Now this section here is problematic for a lot of people. It's difficult, but that's life with chemistry, right? So I give you the concept of what we call an energy diagram. So here's where reactants turn into products and it gives off energy. So here's potential energy on the y-axis, and here is simply the course of reactions as you convert from reactants into products. So it's like this ball or a rock on a cliff. Here I got more potential energy than down here. But I have to overcome this barrier right here before I can drop down here. So if I have a container of gasoline and it's surrounded by oxygen, will that have the tendency to burn? Yes. So that means that we do have this situation right here. But it doesn't just blow up spontaneously. Somebody has to light a match or a spark or something, right? And what that match or spark does is it overcomes that little energy barrier right there. Like on a rock on a cliff, you've got to give it a push to make it roll down the cliff. And that's called the energy of activation, energy barrier. So when a few of these molecules react with oxygen and give off some energy, that little bit of energy takes the rest of the molecules and makes them go over here. Now this energy over here is enough to make all the other molecules overcome that barrier right there. So the reaction turns into a chain reaction and keeps going. Okay? So we call that a spontaneous reaction. Even though there might be an energy barrier there, that's a spontaneous reaction. If you live in a valley and you look up on the cliff and you see a rock, you should be worried about that rock falling down. It's a spontaneous reaction. It's just a matter of when is that energy barrier going to be overcome. Okay. So here's 4 cases where a reaction will occur. When the reaction is shown by giving a number here or known to be an exothermic reaction. So if I look at methane, you guys know that methane will burn. But if you didn't know that and I put energy as a product over here, that tells you that the reaction is going to happen spontaneously. In contrast, the reverse of that reaction is not going to happen. That's not going to be a spontaneous reaction. To get CO2 and water to form methane and oxygen, I have to put that amount of energy in there. If I don't put that energy in there, it's not going to happen. Then again, the solubility rules. So if I look and I see that a product is going to be a precipitate that means the reaction is going to happen. If I see that a product is going to be a gas, that means that the reaction is going to happen. If I look at the activity series for single displacement reactions, and I see a more stable metal on the product side, then I know that reaction is going to happen. So here's some examples of that. So questions so far? So I just made that video on the rest of chapter 12. Hopefully that helps. I hadn't made a video in about a year, so I had to remember how to do everything. And then this takes hours and hours and hours. So for example, that last Zoom meeting that I put up on La Lima, to convert the Zoom video into a usable video took about an hour. And then to upload that usable video to the YouTube took about another hour. Then I had to wait another couple hours for them to actually finish editing it. So it takes several hours to get these things up. So anyway, the mole concept. You already know the dozen concept, so therefore you know the mole concept. A dozen things is 12 things, and a mole is 6.022 times 10 to the 23rd things. And the molar mass is the mass of 1 mole of either atoms, molecules, or formula units. So if you remember, you go to the periodic table and look at the atomic mass. If you talk about 1 atom, that's in terms of AMU. And we call that the atomic weight, or individual mass. But the same number, if I give it the units of grams, refers to a mole of those atoms. And that's called the gram atomic weight, also known as molar mass. So here, I kind of summarized it. So if it's in atoms, and I got 1 atom, that's called the atomic weight, with the units of AMU. If I have a mole of them, it's called the gram atomic weight. And molecules would be molecular weight and gram molecular weight. Formula units, that would be for ionic compounds, FW or GFW. But anyway, these are conversion factors. So abbreviations can be used in calculations, and one thing you need to realize is that when I'm teaching you stuff, I don't want to teach you only the Harry Davis way. You guys are going to be out there taking standardized exams for this and that, and so you may come across these terminology. So that's why you need to know it. So what is the gram atomic weight for oxygen? So that means it's grams. So we're talking about a mole of oxygen. A means it's atoms. So a mole of oxygen atoms. So I go to the periodic table. It's about 16. So 16 grams. What is the molecular weight for oxygen? So there's no G. That means you're talking about a single thing. I mean, the unit should be AMU. And M means a molecule. So oxygen molecules are O2. So I have 2 atoms, and each atom weighs around 16 AMU. So that should be 32 AMU. If it was gram molecular weight, then that would be 32 grams. So watch how this is worded. Calculate the gram formula weight of magnesium phosphate. What if I never told you what gram formula weight was? You would be totally lost. But the gram formula weight is another name for the molar mass. So if I'm looking at magnesium phosphate, that formula tells me that for every one formula, there's 3 magnesiums, 2 phosphoruses, and 8 oxygens. So I go to the periodic table, and I see that the mass on the periodic table for magnesium is about 24 grams in a mole. And I got 3 moles of that. So that means if I have 1 mole of magnesium phosphate, it's going to have about 73 grams of magnesium in it. Does that make sense?
Yes.
What about phosphorus? I go to the periodic table. Phosphorus is about 31 grams in a mole. I have 2 moles of it per molecule, so therefore I got about 62 grams of phosphorus. For oxygen, I got 8 moles of it, and each mole is about 16 grams, so about 128 grams. So I got the mass of this, the mass of this, the mass of this. So when I add those all up, I get the mass of the whole molecule. So we find that 1 mole of magnesium phosphate weighs 263 grams. 1 mole is also the same as the gram formula weight. It's also the same as the molar mass. So that gives us 2 important conversion factors. One mole is equal to that many grams. So here's that conversion factor right here. Is that a direct proportion? What would be different if instead of starting with 1 mole over here, I started with 2 moles? Then everything over here would be doubled. That would be doubled, but that would be for 2 moles. So 1 mole is 263 grams. 2 moles should be twice as much. 0 moles should be 0 grams. Straight line passing through the origin. That's a direct proportion. And what would be different if instead of talking about a mole of magnesium phosphate, I talked about 1 molecule of magnesium phosphate? Then I would have 24.305 AMU per atom, and I would have 3 atoms, and this would be 72.915 AMU. And this would be 263 something AMU. Make sense? So there's another conversion factor. So we can also calculate what's called the percent composition from the same data. So you see how I set this problem up over here? When I do it that way, I can see exactly what I'm doing, and I give myself room for another calculation over here. So the percent magnesium is that I have about 73 grams of magnesium out of the total of about 263 grams of magnesium phosphate. So the percent magnesium is that, which turns out to be about 28% magnesium. Similar with percent phosphorus and percent oxygen, and amazingly, that adds up to be 100%. We'll see later on why percent composition can be used, why it's useful. Okay. So we haven't done any math hardly at all for this unit. So now we're doing math. So what I want to do is organize the conversion factors that you're going to be using. So notice that we can convert between grams and moles of a substance by using the molar mass. We also can take the number of moles and turn that into the number of molecules, or whatever it is, using Avogadro's number. we've used both of those conversion factors before. Now we have a new conversion factor. We can use the formula. So if I look at moles of magnesium phosphate, how would I get moles of magnesium from that? It's right there in the formula. There's 3 moles of magnesium in every 1 mole of magnesium phosphate. So to reiterate, everything about a chemical formula is a direct proportion. Everything about a balanced chemical reaction is a direct proportion. You see why at the very beginning of the class I was trying to get you to solve problems using the direct proportion? Because most things in chemistry are a direct proportion. And we set direct proportions up by looking at the units. And right now, you're going to have to be doing some problems. You need to identify what conversion factors you have. Right now, there's only 3 conversion factors. By the time we're done with this course, there's only going to be 6 conversion factors. So right now, you're using half of them. So what I would like you to do is think of this as a toolbox. These are tools. Every conversion factor is a tool. Right now, you got 3 tools in your toolbox. And just like a carpenter, if you're told, okay, here's a job, put a door in this wall right here, what are you thinking? You're thinking, what tool do I use first? You're thinking, what tool is in my toolbox, and which one do I use first? I want you to do the same thing here. But you got it easy. Carpenter has a truck or van full of tools, right? How many tools in your toolbox? 3. It's like, which one do you use first? That's all. So let's do some problems. So how many grams of magnesium phosphate in 6 moles if the molar mass is given to you? So that's 6 moles of what? 6 moles of magnesium phosphate. So then I need to get that into grams of magnesium phosphate. So what has to be in here? I have to have something to get rid of moles of magnesium phosphate and something to get grams of magnesium phosphate. That's simply the molar mass. So what am I doing? I'm going from here to here using that tool. Next problem, how many moles of magnesium phosphate in 6 grams? I'm simply going from here to here using that same tool. How many formula units in 6 grams of magnesium phosphate? Well, I'm over here with grams of magnesium phosphate. To get over here, I have to go first into moles. Notice that moles is the center of everything. So if you're looking at a problem and you don't know what to do, what do? You go to moles. Make sense?
Yeah.
And then the formula is a source of conversion factors. So how many moles of oxygen in 0.5 moles of magnesium phosphate? So where are we? We're moles. And I want to get moles of oxygen. So how do I get from here to here? I use the formula. Okay. So right here, I got 8 moles in every one of these moles of magnesium phosphate. That's my conversion factor. Okay. So how many moles of magnesium in so many grams of magnesium phosphate? So I got to get the grams of magnesium phosphate, turn that into moles. So what is the conversion factor I need? I need to get rid of grams, keep moles. Well, that's the molar mass. Okay. So I got that many moles of magnesium phosphate. So, okay, why do I have, oh, then they're asking how many moles of magnesium. If I got that many moles of magnesium phosphate, I can see that there's 3 moles of magnesium in every 1 mole of magnesium phosphate. So that gives me that many moles of magnesium. So how many grams of phosphorus? How many grams of phosphorus and 6 grams of magnesium? So what do I have to do first? Go to moles, because that's in the middle of everything. So I take the 6 grams, turn that into moles. Now that's moles of magnesium phosphate. They want moles of phosphorus, so I had to convert that into moles of phosphorus. Then I had to get from moles of phosphorus into grams of phosphorus. How did I do that? How would you get the grams of phosphorus per mole of phosphorus? That's simply the periodic table. So anyway, we end up with 1.41 grams of phosphorus. So now I want to prove to you that everything we're doing is a direct proportion. So I can use this information right here to calculate the percent phosphorus. There's 1.41 grams of phosphorus in every 6 grams of magnesium phosphate. That gives us 23.6%. Isn't that what we calculated over here? You see that? It's all proportional. So knowing percent composition, we can do this kind of calculation. So how many tons of phosphorus and 2 million tons of magnesium phosphate given the percent phosphorus? Remember, percent is a conversion factor. It's also a direct proportion. That 23.6% means that there's 23.6 tons of phosphorus in every 100 tons of magnesium phosphate. So here's tons of magnesium phosphate. Cancel that out. Keep tons of phosphorus. There's the answer. So who might have to do a calculation like that? Maybe this is fertilizer. Maybe a farmer. Do farmers have to know math? Yep.
Yes.
So what is the percent cyanide and sodium cyanide? Okay, well, first, I had to calculate the molar mass. Then I calculated the percent composition. And from that, I can see that cyanide contains all of the carbon and all of the nitrogen. So I added that up. So sodium cyanide is 53% cyanide. So how many grams of cyanide and 500 grams of sodium cyanide? Okay, well, again, I'm using the units to set this up. Okay. So I get 266 grams of cyanide. So who would have to do that kind of a calculation? Maybe a terrorist? Any terrorists out there? Anyone? Oh, I get it. If you were a terrorist, you wouldn't admit it, you'd be on the down low, right? Okay. So here's another use for percent composition. You don't have to do this. It's in a red box. If you took chemistry 161, 162, you'd have to do this. So we can get the empirical formula from the percent composition. So I took this compound and got its percent composition. Then I threw the numbers all over the place because I want you to realize that we don't even have to have really precise, accurate numbers. So what we do is we assume that we have 100 grams of the compound. If we had 100 grams of the compound, we would have 15.4 grams of carbon, 23.1 grams of aluminum, and the rest of it would be oxygen, right? So for carbon, I took that 15.4 grams and turned it into moles. Aluminum, same thing, turned it into moles. Oxygen, same thing, I turned it into moles. And then I put them in the same order that we find on periodic table, right? So going from left to right, that's the way we do it. So H2O, sodium chloride, right? So when we do that, I get this ratio, and I put the number of moles of each one. Isn't that really what a molecular formula is? It is, right? But now I have a problem. It's like I don't have whole numbers. So the next part is simply try to get those into whole numbers. So I would take the smallest number and divide by itself to make that smallest number into a 1. Okay, so I take everything in here and I divide by 0.856. When I do that, I get about, well, that's a 1. That's close to 1.5. That's close to 4.5. Then I think, well, I know I can't have half of an atom, so I'm going to multiply everything by 2. So here, I get rid of all the fractions. So what that means is that there's 2 aluminums for every 3 carbons, right? And then, because one of these is a metal and the rest are non-metals, you could use your vast knowledge of polyatomic ions. What polyatomic ion do you remember that has carbon and oxygen in it? It's carbonate. So you see how that works out perfectly? This unknown substance is now identified as aluminum carbonate. Here's another one. I made it a little bit more complicated. So anyway, these ones I threw the numbers off all over the place. So I used the percentages. So if I had 41% boron, if I had 100 grams of the substance, I would have 41 grams of boron, 52 grams of nitrogen, 7 grams of hydrogen. So I just did that and turned that into moles. Here's the mole ratio. And I look at my data, the data is not good. So I'm thinking, is this 1.8 supposed to be a 2? It might have to be 1.5, I don't know, but I'll try to go with a 2, see what happens. So that was what the empirical formula would be. So then, what if I know some other information? What if I now find out that the molar mass of this substance that has hydrogen, boron, and nitrogen is 80.5 grams in a mole? Okay, well, I'll check. I calculate the molar mass of the H2BN, and I get about 27 grams in a mole. But that 27 grams per mole is nowhere near the 80.5 grams per mole. So what I do is I take the ratio, 80.5 grams per mole and 26.8 grams per mole. The ratio there is 3. So that means I have 3 empirical units in my molecular formula. So this is now the molecular formula. And here is the chemical structure of that. Okay. So anyway, That's not going to be on the exam or anything. I think that's just for your own knowledge. So from here on, the rest of this chapter is not on the exam. So here I'm showing you a very important use of percent composition. And then the rest of the chapter, I'm trying to emphasize that knowledge of chemistry is knowledge about yourself and the world you live in. So we were talking about solubility of different things, right? So here's a kidney stone. Here's a uric acid crystal. Uric acid crystals give gout. Okay? Kidney stones are kidney stones. Anybody ever have a kidney stone?
We're too young for kidney stones.
So far, for now. I had a woman tell me one time, oh my God, I had a kidney stone. It was so painful. It was way more painful than having a baby. And I'm like, okay, well, I'm not able to make that comparison, but it looks like a piece of coral, doesn't it? Passing through your urethra.
Oh, jeez.
This is the reason why you're supposed to drink a lot of water, so you don't get these crystals forming. Okay. So gout comes from metabolism of purines. That means if you eat a lot of DNA and RNA, you're going to get a lot of purines. And so I want to talk about this inhibitor called allopurinol, which is a drug. I've actually know a couple people that get gout easily. They take allopurinol to counter it. So here's an enzyme, and what it does is it takes purines and turns them into uric acid. So uric acid is what gives you gout, right? These needle-like crystals over here. So what you do with the allopurinol is, allopurinol goes in here, and it's very, very similar to hypoxanthine and xanthine. So the enzyme gets confused. Whenever it binds allopurinol, it can't do anything with it. So what you're doing is you're delaying the production of uric acid so that your body has time to get rid of it, so it doesn't build up in such high concentrations as to precipitate in your body. And look at allopurinol. You see the C and the N right there? They switched it. So normally the N is here, the C is here. To make this drug, they had to figure out how to switch those two atoms. Okay. And people tell me that it's very, very effective. So, gout can be avoided by drinking a lot of water to avoid dehydration, reducing foods with excessive nucleic acids, like a list I gave there, and that includes fructose. So I want to go into what is high fructose corn syrup? Does it have a problem? Does it give us a problem? So again, here's sucrose, table sugar. When you hydrolyze it with an enzyme called sucrase, you get fructose and you get glucose. So common table sugar is 50% fructose. So, I can let you look at those cartoons in a minute, but let me see if I can find the, yeah. Is that still showing up on the screen?
Yes.
Okay. So this is an introduction to a metabolic pathway. So glucose comes into the cell, and the amount of glucose in the cell is highly regulated. When glucose gets into the cell, everything about it is highly regulated. Look at these two enzymes right here. So fructose 1,6-diphosphatase is turned off by glucagon, turned on by insulin. This enzyme over here is turned off by ATP and turned off by citrate. My point is that glucose metabolism is highly regulated. Biochemists like myself, when the fructose problem first came up, we like, well, no, that's not a problem because it goes right into glycolysis. But at first, we didn't realize that fructose comes in, and before it goes into glycolysis, it's unregulated. So fructose comes in, it can come pouring into the cell at high concentrations, and the first step is it's converted into fructose 1-phosphate. So you can see two places here where ATP is being used. So here's the problem. If you have too much fructose coming in and it's unregulated, you'll take all of your ATP, turn it into ADP. Now the concentration of ADP is very high in the cell, and that could activate the decomposition. So ADP gets dephosphorylated, turns into AMP, goes through a couple of different pathways, and guess what the final product is? Uric acid. So my point is this: too much sucrose, too much fructose in your diet could potentially give you gout. Now, you say you're too young to get gout.
No, I didn't say that. Is it the same as kidney stones?
Yeah, it can happen, really can, with dehydration and stuff.
Yeah, yeah.
So here's the problem. You may not get the symptom of gout, but high levels of uric acid can cause what's called generalized edema, swelling of tissues. And what does swelling of tissues do? Reduces blood flow, especially into capillary beds, especially into extremities. That's a major problem that happens with diabetes, isn't it? They lose blood flow to their extremities. That now puts pressure on their heart and everything else. So going back to what I've always said about anything, no matter what kind of food, no matter what kind of vitamin it is, everything should be in moderation. When you go drink a regular soda, regular sweetened soda, that is not moderation. That's an extreme amount of fructose and glucose, not fructose and glucose, but fructose and sucrose going into your body. That's extreme.
Is uric acid the what's it called?
It's the byproduct.
The byproduct from only like sugar, or is it from something else too? Because can't you get gout from like eating like rich foods and stuff?
RNA, what gives you gout.
Oh.
So like say for example, you get gout from eating shrimp
Mm-hmm.
or mushrooms. The reason is those two organisms are extremely active. They're making RNA all the time, constantly regenerating their cells. So there's lots of RNA and DNA. And it's the purines from the RNA and DNA that end up giving you the uric acid and the gout. Anyway, if I had my way and we had more time, then I would constantly be doing these references to things that are important to you, and kind of my goal. Does anybody have any questions about anything? Politics? Boyfriends? I told you already, get rid of all the boyfriends because all they do is they interfere with your study time.
It's so true. Thank you. It's so bad. Did you change quiz dates? Because I see that you sent an email. Weren't they already all due on the 4th? Or you changed?
I'll change it to the 4th. What I'm noticing is that students are behind in doing their work. And I don't know if it's truly because of the virus and everything or just because they'd be behind anyway, but
Yeah.
I'm going to give them the benefit of the doubt and hopefully they'll catch up. And
Yeah.
I'm going to figure out what to do with the exam, but the exam has to be sometime next week. So,
Okay. I think probably everyone's just trying to adjust, I would say.
yep.
Yeah.
Are we gonna take in the STEM center? Or I mean, sorry,
Testing center-
library?
Nope.
Okay.
Nope. So what some testing centers have expanded their capabilities, others have just closed down. And all of them have said that they're only going to do their own students. So if you're a KCC student, you can't take it at any other testing center now. So in other words, testing centers are just out.
Okay.
Proctor U is out. Pretty much everything is out. So they're leaving us to our own invention, so to speak.
My other professor is just doing like timed questions, which kind of sucks. It's kind of harder for you because we have to do math problems. But she's like giving us 60 seconds per question to like try and, I don't know, regulate. But yeah, it's harder for you because some questions are math problems on yours and some are true and false and stuff. So,
Well, I don't like students being restricted to a timeline anyway.
yeah.
I myself am quite dyslexic, so I have a hard time reading and doing all this kind of stuff. And yeah, so I would prefer that everybody had ample time.
Yeah.
I don't like to time things.
Yeah, me either. Well, then plus you can't go back and check your work. It's like once you submit, it's over.
So I'm still trying to figure out all this stuff. I am on that system-wide committee, and we talked about it a little bit today, and there's no resolution. Resolution is that we're in a predicament, and we just got to suffer through it.
Don't call it that, suffer.
Okay.
Adjust, adapt.
Adjust. Yeah.
Have you been recording these and posting them on La Luma? Because I've just been.
Yes. Mm-hmm.
Okay.
Yeah. So this one, as far as I can tell, is recorded.
Yeah, it's still recording.
And yeah, I try to leave out a lot of the bad jokes and do the business. What was that? Kids' voice.
Kids, yeah.
Yeah, sorry, that's my son.
Okay, well, if you have other questions, you can always email me. Well, I prefer you to do
Bye, mommy teacher.
discussion, on La Lima. Discussion and private messaging. I don't care about the private messaging. That's the same as email. But when you have a question, you put it in discussions and everybody has the opportunity to see it and can benefit from it.
Okay.
Yeah. And I do check those all the time. Then I see that nobody adds any questions and then I get all depressed.
Okay, I'm going to try to add one for you today.
Okay, thanks so much.
All right, thank you, Professor.
Okay, you guys have a good day, okay?
Bye.
Thank you.
Here. Stop video.
Oh, hello. Oh my gosh.
Close the darn thing.
Hello, Professor.
Yeah.
Yeah, I want to check my feedback from exam 2. Like, I don't know what, like, why I get wrong, and what question I got wrong. So
Okay, well, normally I have students do that in the office, and I just
yeah.
open up on my computer, but I don't know how to do that now
Oh,
because,
okay.
yeah.
Yeah, I'm just worried for the last exam because I want to know what my mistake. So
Yeah, I don't know how to do that. Yeah, sorry.
yeah, it's okay.
I'll think about it, see if I can find a way, okay?
Yeah. So it means we will take the exam online.
Yep, it'll be online somehow. Not sure how it's going to happen.
Oh yes, yeah. Thank you so much.
Okay, you take care now.
Yeah, you too. I see you on Monday.
Bye. Come on, how do I turn this off?